Marie asked me to give you an introduction to ocean color and climate. So, and I thought I will base it on this big initiative launched by the European Space Agency called the Climate Change Initiative. And it has an ocean color component in it with which we are heavily involved. So some of you at least might wonder what color, and that too of the oceans, has to do with climate. It's more obvious if you are talking about temperature, sea surface temperature, climate, it's increasing, so that's something to worry about. Or sea level increasing, we know why, we know it's a problem. But why should we worry about ocean color in the context of climate change? And if I can get this to work, no, try this. Okay. The reason is that the color tells us something about how the light that is available for sustaining life in the ocean is in fact coupled to the marine ecosystem. As Trevor mentioned in his talk, this coupling happens at the level of phytoplankton pigments. And these pigments are green, and pure water is blue. So the more phytoplankton you have in the water, the more the color changes towards green. So if you look at an image like this, as Trevor said, this is not, can I point? No, none of this is really doing it for me. Okay. If you look at an image like this, and as Trevor mentioned, this is not true color, but false color applied to enhance the information. But but regardless of that detail, oh, thank you. It was not turned on, is it? Can I still get that? It moves. And anyway, so I need to still go back. So when you see the change in the color, and the more green the color, what it is telling us is that in those locations, the sunlight, the energy source, and the marine ecosystem are more strongly coupled together. The information that you are getting could not be more fundamental than that. And that is what you are getting from ocean color. So if we accept that climate is not just about physical climate, but also about how life on our planet is responding to, or to some extent even modifying climate, then we could not look for a better source of information than this. So as Trevor mentioned again, the chlorophyll A concentration, which is the concentration of the phytoplankton pigment that is most commonly associated with photosynthesis, and that is a property that we can get from ocean color. So I can list other reasons why phytoplankton should be included in ocean color. Maybe you will ask me when we can, I'll tell you why. But anyway, for these and other reasons now, ocean color and phytoplankton are now recognized as essential climate variables by the group, what is it called? The Global Climate Observing System, which is a committee that is overseeing the observation of climate and climate change. So the Ocean Color Climate Change Initiative, initiated by, which is an initiative of the European Space Agency, charged all the participants, including Ocean Color, to do the following: identify user requirements. What do users want from ocean color data? Then, if you know what they want, then compare candidate algorithms that best meet the user requirements, and then select those ones for your processing. Then establish uncertainties in the products, because as I was saying earlier, it's important for us to know not just what ocean color products are telling us, but also the uncertainties associated with those products. And this was a big challenge. Tell us that on a per pixel basis, every location where we have a satellite product, tell us also how much confidence you have in the product. Then we had the engineering part of it, generate software for producing all this, and then generate the merged time series for as long a period as possible, and then assess quality and validate the products. And it turned out that it was a monumental task, and when carrying it out, we had help from a huge group of people, the broader community, helping us in a variety of ways, giving us in situ data to validate the products, giving us feedback on the products, participating in the algorithm comparisons, and so on. So that was just to tell you how at every step of the way, we reached out to the user community and then collected their feedbacks. And one of them was this workshop that was held last year in Frascati. So how does this ocean color product that we have generated for climate studies look? We started with 3 sensors: MODIS Aqua, MERIS, which is a European one, this is a NASA sensor, and CEVIS. So when we were merging, we took the individual sensors, then we brought them together. And at this stage, we compared the differences between the sensors at the level of the remote sensing reflectance at the sea surface, where there was overlap between the sensors, to identify inter-sensor biases. But before we could do the bias correction, there was another problem to deal with. So far, all the ocean color satellite sensors that we have access to had different waveband sets. So it was difficult to see if there was any difference, because you're looking not at quite the same things. So we had to apply some models and shift the bands to a common set. Then we could look to see if there were differences. And we chose CEVIS as our reference for a number of reasons, including the fact that this was the first sensor to which we could refer back to. The other was, at least at the time when we began the work, this was the sensor that we were the most familiar with, the most understood, and it made sense to refer everything back to CEVIS. So the idea then was that we would take MODIS and MERIS, shift the bands in these using the same underlying optical models that went into the algorithms, and then shift them to the CEVIS band set, compare them where there are overlaps, and then identify inter-sensor biases, correct them, and then you merge them. So the other thing that we did was we also, as I mentioned, did a very detailed algorithm intercomparison to decide at every step of the processing chain which algorithm served us best. So for processing some of the satellite sensors, we chose an algorithm called the polymer. It doesn't say anywhere. Anyway, this algorithm, which is a relative newcomer in the field, had the added advantage that it improved coverage of the products, mainly because it is able to retrieve usable signal under sun glint conditions. Trevor mentioned that it is ocean color sensors are passive sensors, which means that they only work under clear sky, sunlit conditions. But at the same time, if the signal from the sunlight is too strong, then also you are limited in what you can retrieve from the ocean. For example, under sun glint conditions, when the reflected light from the surface of the ocean is very strong, typically you discard that signal because the surface reflection overrides what you can get from underneath. But polymer is able to correct for that and therefore improves the daily coverage. Then I mentioned that we were also charged with making sure that we validate the products and give quality assurance on the products. So how do we do that? If you want to do uncertainty estimates, there are several ways in which you can do it. But when we consulted the users, they said we want to know how well satellite observations match in situ observations. So a chunk of our effort went into collecting in situ data, and this shows how over the years our in situ database has improved because we've been able to build on contributions from various people who were the ones who said they liked collecting data so do contribute to global initiatives like this. So then we use all that data to arrive at some estimates of how well the satellite products match in situ observations, chlorophyll in this case, but the Ocean Color Climate Change Initiative also gives out other products, absorption by CDOM, phytoplankton, diffuse attenuation. Each one of those products has undergone comparison with in situ observations like this. The exception is information on backscattering, and that is because the database of matchup information between ocean color products and in situ measurements of backscattering is so poor that we didn't feel we would be justified in giving some estimates of uncertainties. So if you're into making in-water measurements at sub-zero temperatures, make sure you're measuring backscattering, okay? But okay, this kind of a comparison only tells us what we can say about the quality of the product at global scale. On the other hand, we were asked to produce estimates at the level of every pixel. So how can we go from this to a pixel per pixel uncertainty estimates when you don't have uncertainty or matchup estimates at every pixel directly? If you had it, you won't need the satellite, so you have a conundrum there. So the way we approached it was as follows. Oh, I should skip. Okay, this one. In the first place, we used an optical classification to classify every pixel as belonging to one or more of 14 optical classes. I say one or more because the classification is a fuzzy logic classification which tells you if a pixel is similar to one or more class, which is called the membership. So that's one part of the problem. We classify each pixel according to its membership to different optical classes. In the final set that we made, there are 14 classes all over the entire globe. Then the in situ matchup data that we had, we partitioned into all these 14 classes. Then we established uncertainty estimates for each class. Then we assigned uncertainty to a pixel depending on the membership of that optical class in that pixel. So this was the strategy that we used to go from a global quality assessment to a per pixel assessment. In the OCCCI, the uncertainties are root mean square difference, that's shown here, but we also provide estimates on the systematic errors or the bias. When you do this kind of a global estimate and you are making extrapolation left and right, it's also good to see whether you have made a decent job of estimating uncertainties in the products. So we also try to do that. This is from a paper, Mellin and colleagues, where we compared our own estimates, OCCI, with other ways of estimating uncertainties, whether it be from comparison with very rigorous in situ measurements where they existed. This is a MOBI time series observations in the middle of the Pacific, and this is in the Mediterranean. And we also try to arrive at uncertainty estimates by looking at variability within sensor products and between sensor and so on. And I think we are beginning to find consistency between different estimates of uncertainties. So the GCOS committee that I mentioned, the Global Climate Observing System, they said what they needed from ocean color, but they also said with what accuracy they needed the products. So now we have uncertainty estimates. We can begin to compare the relative error in the products on a per pixel basis. So this is a frequency distribution, and then see whether that meets GCOS requirements or not. And this is an earlier version of our products, version 2 and version 3. And we see that at least in some of the products, we are meeting GCOS requirements for accuracy. But it's not true of all the products. For example, RRS or remote sensing reflectance at some wavelength, in some locations, we do fall short of GCOS requirements. But this is the way we think we can make progress. You identify what's possible now, you identify where we are falling short, and if you go back to this kind of a classification, you know which are the locations where we are beginning or we are not doing so well. Then you can begin to focus on in situ campaigns to those regions, to those optical classes, so that in future we can keep improving. Okay, the other thing that we have done in this in the generation of this product for climate applications is to blend algorithms according to optical class. This is because we know that, well, at least we think we know, that we don't yet have a perfect algorithm that works well in all types of waters. So when we did the comparison of algorithms available for generation of, say, chlorophyll concentration or in water inherent optical properties and so on, we did the evaluation of algorithms for each optical class. And it turned out that in some optical classes, open ocean, certain algorithms performed best. And when you came very close to the coastal waters, some other algorithms performed better. So once again, we assigned algorithms according to optical classes, and then we blended the algorithms according to the membership of each class in each pixel, so that you generate this kind of a product where, as you go from open ocean to coastal ocean, the algorithms that are applied changes. And this is our first effort, shall we say, to improve the products towards the coastal areas where so-called case 2 waters appear, while at the same time avoiding sharp boundaries where you switch from one algorithm to another. So it's a blended algorithm that avoids sharp discontinuities. So, how does this look like? If you go to oceancolor.org, Maria, are we going to have some practicals where we go to this website? Tomorrow. Okay. So if you go to oceancolor.org, you will get daily, 5-day, 8-day, and monthly products. And like I said, each one of those products will have associated bias and uncertainty estimates. So it's all there for you to use. It goes from the time when CVIFS was launched, September 1997, to end of 2015. And we are working on extending it. It will be extended at least to the end of 2016 in due course. And for those who are more into the processing side of things, the processing chain looks like this. We take level 1 products, and I said we started with these 3. We have now added vias, and they all go through the atmospheric correction, band shifting, merging, bias correction, and then the products, quality control, uncertainty characterization, and then it's going to the user community. And there is this growing global database. By the way, any of you interested in that database, it's now publicly available. Okay. So, when it comes to generating this type of a time series from Ocean Color for climate studies, as I mentioned earlier, one of the big problems we faced was these differences in the visible bands that were available for ocean color data analysis. That's a CVIF set, MODIS, Aqua, MERIS, and VIIRS. So merging them was a big task which involved this bias correction, band shifting, and all that. But right now we are entering a new era with the launch of Sentinel-3 missions, because the OLCI sensor in Sentinel-3, and then it will be in Sentinel-3B and 3D and so on, they will all carry the same sensor. They say 20 years, but I hope it will be forever into the future. And it's mostly consistent with MERIS. So for the first time, we are in a position where we can think of these sensors as a sort of continuous reference for us in the space, so that every other satellite that's launched, we can compare against this long time series. And there will always be 2 sensors in orbit at the same time. When their mission is completed, there will be 3A is launched, then 3B will be available. So 3A and 3B will be in orbit at the same time. So that means you can compare 3A against 3B, correct for any instrumental differences, without having to worry about how good a job you're doing when you do band shifting before you can do bias correction. Then before these are die, the idea is that 3C would come and then 3D and so on into the future. So, sorry?
What's the difference between 3A, 2B, 3C?
No difference. It's only a same instrument launched a bit later. That's the idea.
So there's no difference at all?
In principle, no. In practice, there will always be some difference because there are two instruments. But because they are going to be up in space at the same time, and they are monitoring at exactly the same wavelength, same everything, you would be able to compare them a lot more easily and see if there are differences and easier to correct for them. Did I see another hand? Yes?
I just want to ask that whether for the merging, whether the reduced resolution of mirrors was used or full resolution, FRS or the RS.
We use reduced resolution. I don't know if I think I didn't mention, this is a 4 kilometer resolution product. So we went with a reduced resolution to be able to get the global thing. We are looking into 1 kilometer resolution. It multiplies our problem by a factor of 16, not trivial. But at the global level, we are not yet talking about doing full resolution mirrors or Sentinel at 300 meters. Maybe at regional scales, but not at the global level. Okay, yes?
How many years of data do you think you need before you can start to look at climate variability?
Okay, it's a good question, and papers have been written about it and get cited too. But I think the answer is quite simple. The oceans are under the oceans experience oscillations and variability at multiple timescales. The important ones in this context are the ones that are of decadal timescales. So if the oceans are subject to oscillations at decadal timescales, then 10 years is not enough. Easy to say that you at least need 30 or 50 years. We are at 20 years. So I will show you some trends and things if time permits, but I would like you to remember that is not climate trend. We are still looking at variability. So all we can say is that we have begun a process by which you should be able to detect a climate signal as and when it appears. So there is that problem. In the first place, you have to have a time series that is long enough to detect climate. You could say that, you know that in the oceans, the spatial and temporal scales are correlated. And the closer you come to coastal waters, smaller gets the time scales that are relevant, also spatial scales. So it may be that we are close to getting to the level where you can look at climate signal in some coastal areas or wherever, but you have to be very careful that you have eliminated any oscillation at the appropriate time scales before you detect what you might call a climate signal. Okay? Anything else? Yes?
You mentioned before you were showing a product, a blended product that you did. You say you move all the frequencies to the C wave. I mean, you're using all the frequencies on the top.
Yes, the product will have RRS values at these wavelengths.
And all the references in the second and third row are moving to the top.
Yeah, moving to the top one. But bear in mind that we are only, most of the time, we are shifting very small wavelengths. This is 412, and this is 412.5, and this is 410. So we're talking about narrow shifts. And 531 is a problem. 510, 510, 490, 490, and this is 488 to 490, and so on. So for the most part, we have tried only to do small shifts. When we come to Meris and Sentinel, the problem is more severe. Sorry, you were still asking me.
At the end, you lose resolution.
We use resolution in the interest of generating a long, consistent time series. Okay. So the other advantage, in principle, going forward, is that now, backwards or forwards, this one. The advantage of the Sentinel-3 is not only do we have consistent time series, we also have improved resolution. Okay? So going forward, we should be able to do better. Spectral resolution. Whereas CWIFs had 1, 2, 3, 4, 5, 6 wavebands, now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It gets more complicated. Some of these wavebands are designed for looking at chlorophyll fluorescence as opposed to chlorophyll absorption. And doing things with fluorescence is a lot more difficult than doing things with absorption. In principle, you have better resolution, better everything. Going forward. Now, if you want to go backwards to CWIFs, then it becomes a problem. So anyway, what we think we might do is going forward, you retain all the Sentinel-3 bands. Going back to Meris, maybe we can do the same set, except maybe 400. But that's also a problem, because Meris died, when was it? 2012? And this one came out 2015 or so, last year, no, a little over, yeah, maybe 2015, I think. So we have a gap. So how do we jump the gap? So it's not easy. I think things are looking better going forward, but not so good going backwards if you want a consistent set of data. So, as I was saying, Sentinel-3 is a big improvement for us. There is the consistency in the constellation of satellites. There is a more or less consistency with Meris, except for one waveband. And now we have promise of continuity for the first time. Up until now, every sensor was different. Going forward, at least the Sentinel series will be consistent with each other. And because there will be at least 2 sensors in orbit at the same time, we also anticipate that the daily coverage would be better. And the improved spectral resolution that we have been talking about also implies that we can, in principle at least, do better atmospheric correction and also possibly develop and implement novel algorithms that will exploit the additional wavelengths. And the good thing about the Sentinel mission is that between ESA, European Commission, and EUMETSAT, the ground segment of the mission also includes high quality in situ data acquisition for product validation. But as I mentioned just now, the gap between OLCI and Meris is a challenge if you want to extrapolate or combine, merge things backwards, exploiting the full spectral potential or capability of OLCI. And from the climate perspective, before we can bring OLCI into the time series, we have to go through the same rigorous algorithm evaluation, sensor performance evaluation, and so on, to make sure that it is climate quality before we begin to bring it into the time series. So these are some of the candidate algorithms. This is the standard product that you now get from ESA. This is the polymer product, and so on. And this is the Weir's product now. So you can see that if you are able to add Alchi product into and merge it with Weir's, you'll have definitely an improved coverage and possibly improved quality. Right now, we are limping along with Weir's and MODIS. MODIS is a very old sensor, and by now it's also an ailing sensor. It has some problems with calibration and so on, and NASA is trying their best to keep it calibrated to sufficient quality. But sooner or later, we're going to have to abandon MODIS for this application. Then we'd be entirely dependent on Weir's for now, unless we are able to establish that we can bring Sentinel-3 into this time series, which we think we can. It just needs time. Part of the problem is, again, a sufficient number of in situ observations for validating Alchi products. Marie, shall I carry on for a bit longer or stop?
You have until 1:05, so another 10 minutes.
10 minutes, shall I talk or you want to ask questions? Keep talking? Yeah? Okay. So this is, Bob Bruin is not here and all the others, but at PML they are also involved in these large-scale ocean observation from ships. This is the AMT-19, Atlantic Meridional Transect. That's also true. But then I had to sit down, you see. Anyway, I'm sitting down as it is. Trevor? Sorry, I seem to be quite able to make mistakes whatever I try. Okay. So on the AMT cruises in the recent years, there is a big effort on collecting in situ data for validating satellite products. And the one that this one talks about is from one of a couple of papers from Bob Bruin and Giorgio Dall'Almo, where they have put in place an in situ instrument for continuous monitoring of phytoplankton absorption in the red. That they calibrate against chlorophyll from the reference method, which is the HPLC method. And once that is done, they get a lot more data that they can use for validation of the products. Not only that, because it is done in continuous mode, you are also able to incorporate information on sub-pixel variability in the data. Anyway, the consequence of all that is they report that when you have high quality in situ data for comparison against the satellite data, the uncertainties in the products go down considerably. So the idea here is that if when your in situ data improve, your validation shows that your satellite is performing better than you thought, indicating that at least to some extent the uncertainties are associated with uncertainties in the in situ measurements. So the better you can do your in situ measurements, better we can validate the satellite measurements. Okay, so this whole thing what do I want to say? The whole effort at bringing together such a time series for climate applications would be useless if nobody used it for anything. So within the short time I have left, I'll show you some examples of what people have been using it for, this data set. First is using the data set for looking at trends. So as I mentioned earlier, we have brought together 4 different sensors to create the time series. So how do we know that we didn't create artifacts in the trends? Because the sensors were a little bit different from each other. So to test whether that happened or not, what we did was we took the OCCCI data for the time period when CWIFS was operational, and we looked at the single sensor product, that is the CWIFS time series, for that section of the time series, and compared that with the OCCCI product for the same time interval. Then we can compare them and show that they'll give you the same information. Then we shifted to the Modice period and did the same comparison and showed that those two match. So, but also bear in mind, when we shift the time period, some of the big trends are also reversing signs. Another reason, going back to an earlier question, we are not looking at climate trends, we are looking at climate variability. And these are not seasonal trends. Seasonality has been removed before looking at trends. So now, if we, after satisfying ourselves that we have not introduced artificial trends in the data by merging, we can now, in principle, look at the time series, for this whole time series now that we have 97 to 2015, and it looks like this. But bear in mind, I still don't want to advocate that this is a climate trend. This is the trend for that period, and I'm pretty certain that a lot of the signal is dominated by the huge El Nino event that we had in 2015-2016 period, and another big one that we had at the beginning of the CWIFS period. This image shows you that while the OCCCI product is consistent with CWIFS over the CWIFS period, we see that another product that is available, which is also a merged product, gives you quite a different trend for that time interval, which shows that such products that have not been subjected to rigorous quality evaluation for climate studies should not be used for climate applications. Just be careful if you want to do that. This is another European product. So if this is climate variability, then as biological oceanographers, what you would like to know is why these trends might be positive in some areas, why it might be negative in some areas, and so on. And that is what Marie looked at in one of her papers, where she looked at the positive changes and the negative changes, and then related those observed trends to variations in the physical forcing fields. So she was able to show that the effect that you see will depend on whether the upwelling increased or decreased, and whether river runoff increased or decreased. If you are interested in going into that in more detail, please talk with Marie. But what I would like to emphasize here is that unlike temperature or something where we can say it is increasing globally or whatever, for the biological fields, the importance is to recognize that the effect is not going to be the same everywhere, and it will very much depend on how the local physical fields are changing. And as if not all, as most applications of biological oceanography are regional in scope, for example, fisheries applications, you need to understand what is happening and where it is happening. And satellites are a big tool for looking at that with the resolution that you need at regional or global scales. Maybe I should stop here. Have more examples. I did want to show you one. Maybe I don't have it here, or do I? No. Okay. I'll stop here and answer questions. Okay. Yes.
You said that the Sentinel-3 is now looking at fluorescence instead of absorption, which is
In addition, not instead of, in addition. Let's go back to those bands. Where did I have it? Somewhere here, right? Okay. So the blue-green sensors are always or typically designed to look at absorption and affect or detect whatever is going on through the impact of the constituents on absorption. Absorption that affects reflectance. These bands now, 681, 673, and 708 or 705 in the case of MERIS. Those are the wave bands that are designed to look at fluorescence. 681 is assigned selected to be close to the maximum of the fluorescent signal from chlorophyll. And 673 and 706 are on either side of the chlorophyll fluorescence band. So the idea is that this will let you produce a baseline above which the fluorescent signal is present. So then you can get what is called a fluorescence line height. We don't have a scribbler, right? We can't do a whiteboard scribbling. Anyway, so that's what that's designed for. These three. Yes.
And what is the difference between Sentinel-3A, B, C, and D? And why should we merge the data?
Okay. First question, what's the difference? The answer is no difference. That's the whole point. When you want to create a long time series to look at trends and climate signals, there is no way you can do it with a single sensor, because one sensor may live for 5 years, 10 years, and we are trying to generate a time series for 50, 80, 100 years. So you can never do it with one sensor.
So the difference is 3A was the first, 3B was the second?
Yeah, 3A is the first.
Between them.
No difference between them.
And what about special resolution?
No difference in the spectral resolution. They will carry the same
Special resolution.
spatial resolution, same thing. They have 300-meter resolution.
The only difference is the overpass time.
Sorry?
The only difference is the overpass time.
Overpass time will be different, and the launch time will be different. But if all goes well, there will always be an overlap within the difference of the launch. Even then, there will be some overpasses that are almost instantaneous. I think if the swords come together, that's also planned. I don't know what they quite decided, but when 3B is launched, they're going to put it in a slightly different orbit to have better matchups with 3A, so that you can characterize B very tightly against A, and then it will put it in its planned orbit. So that's planned. You have to keep your fingers closed that it all works. We all need it.
This might be a bit basic, but if you put the second one up, Sentinel B, and then you see that it's giving completely different chlorophyll A reading to Sentinel A, how do you figure out which one's right?
Then you need the in situ observation.
Okay, so you just have to compare it. Okay.
Yes. I don't know if you can ever do away with in situ,
Right.
but that's, if you think about it, that's true of any observation.
Yeah.
Never mind satellite. If you're doing a lab experiment, what do? First thing is you calibrate your instrument. So you do the same for satellites. Yes.
With the in situ stuff, I presume it's limited just to measurements that are made during the daytime to be able to have that match over the satellites, or can you make use of measurements that are made at night and kind of apply corrections or something?
You could, well, in principle, you would, well, it all depends on what kind of compromises you're prepared to make. It comes down to that, really. When in the NASA protocol for validation, I think they have set a 3-hour window. So you have to have your observation within 3 hours of the satellite overpass to make a validation point. So with that kind of tight requirement, you also reduce the number of points you have for validation. Now, in the case of a merged product like this, we are merging satellites that had different overpass periods. So there's already a time fuzziness in the product, because the only resolution we have then is a daily resolution. So in validating the CCI products, we have used daily resolution, for better or for worse. The advantage is that then you increase the number of points, and then if you have sufficient number of points, you hope that you eliminate some of the noise coming from the mismatch. Yes?
I'd like to know, as in the previous lecture, it was told that we can classify the phytoplankton with the help of satellite data. Like we can have micro, nano, and phytoplankton distribution with the help of satellite data. Can we classify suspended sediment or any kind of suspended matter like that in terms of grain size with the help of satellite data?
Aditi, that's for you to do. No, I'm only half kidding. The point is that I mentioned that you can get backscattering, okay? And the backscattering signal, and especially the spectral slope of backscattering, is related to some extent to the size structure of the particles contributing to it. So there is actually more than 2 or 3 papers by this scientist from the US, young dynamic guy, Kostadinov. And he has put in place a method to get at the particle size structure or size distribution by looking at the spectral quality of backscattering. But he has done it for open ocean waters, and having done that, he goes immediately to phytoplankton size structure, saying that phytoplankton are the dominant contributors to the signal there. And I know in your case you want to do it for suspended sediment load in very turbid coastal Indian waters. The problem becomes a little more difficult. But that would be how you go about it. Very often the signal at 676, thereabouts, 673, whatever, that's often taken as a measure of suspended sediment load. I think for Indian waters, there are many people who have calibrated that signal against suspended sediment load. But if you want to take it beyond that to the size distribution, then there is some work to be done. Okay?
What was that scientist's name?
Kostadinov. Kostadinov. something like that.
You mentioned that for the training the product, you use 18 class, like different.
40, yeah, why not? Yeah.
You can see that the global linear analysis that you did is better for the version 2 than version 3. And when you see the spatial distribution of hero, it's better for
Sorry, I'm not sure. Follow you. We have the optical classes.
Yeah. When you say you blend the data, you use 14 classes.
I think it's for uncertainty.
It's for the uncertainty estimate. See, we go let me see if I can go backwards. Okay. At each pixel, we have the RRS remote sensing reflectance values at 6 wavelengths. That is what is used to classify the optical class.
One of these 14 possible.
Yeah, using that, the spectral shape of the RRS spectrum is analyzed to see which class it belongs to, which of 14 classes. And because you are using fuzzy classification, you can establish similarity with more than one class.
So you cannot increase the number of classes.
The classification is done first. You select representative spectra from all over the globe. We use the Longhurst provinces and collected samples from all those, and then you subject it to the classification scheme. So then you get 14 classes. You fix those 14 classes. Then for every pixel in the image, you see which classes that spectrum resembles.
If the number of classes can be increased, will the resolution increase or the accuracy of the product will be better?
Not necessarily. There are few things to remember. You only have 6 bands. So that would set a limit on how many classes you might possibly imagine. If you then increase the number of classes beyond what is reasonable, then one class will begin to look too much like the next class. There'll be too much overlap. So then you don't know which class is really present and so on. So you want to you determine the number of classes to avoid too much overlap between classes and to be sufficiently big so that some pixels are not going unclassified. It's a compromise between those two conflicting requirements. So the other problem is if I now say I have 100 wavebands and I will fix 100 classes, then you need in situ data in sufficient quantity in each one of those classes to establish your uncertainty levels. So if you don't have enough in situ data, you also have a problem. Okay.